Good example to you all. In this video, I will be talking about armature winding. Armature winding is used in every rotating machine, and we cannot limit it up to DC machine, as it is used in AC machine as well as synchronous and asynchronous machine. So here I will be talking about some of the terms related to armature winding. Uh, Firstly, we have conductor, the pair of wire that effectively takes part in electromagnetic energy conversion under the influence of magnetic flux is known as conductor. So out here we can see that these two parts will be exposed to magnetic flux in the machine, and EMF will be induced in it. So these two parts are known as conductors. Next one we have is tune. A tune is made up of two conductors which are joined together by means of extra conductor material known as overhang. Where is coil? When multiple turns of wire are made, it is known as coil. So when coil consists of many turns, a part of the coil in each slot is called as slot side of the coil. So if you talk about EMF induced in one turn, it is equal to 2 times the EMF induced in a conductor, because one turn will consist of two conductors. Next we have is coil span. It is the distance between two coil sides separated by number of slots. Next term we have is short pitch coil. So before talking about short pitch coil, let me talk about pole pitch. It is the distance between two adjacent poles, and one pole pitch is equal to 180-degree electrical. So to calculate pole pitch, we have the formula number of slots divided by number of poles, and pole pitch is denoted by N. So as we know what is pole pitch, so uh, short pitch coil. If the coil span is less than 180-degree electrical, then it is said to be short pitch coil. The next term we have is full pitch winding. If the coil side in one slot is connected to a coil side in another slot, which is one pole pitch distance away from the first slot, the winding is known as full pitch coil. And if it is not one pole pitch, then if it is less than one pole pitch, then we say it as fractional pitch. Like if the pitch of the figure is placed from 1 to 7, if the conductor is placed between 1 to 7, it is known as full pitch, which will be equal to 180-degree electrical. But if it is placed in 1 and 6, it is a fractional pitch, which is 1 to 6, which is less than full pitch winding. In this figure, if you talk about full pitch and short pitch, out here we can see that the full pitch is 7 minus 1, which is equal to 6. So this blue winding forms one full pitch. But if it is less than 7, and if the conductor is placed in 6 slot, then it is known as fractional pitch. Next term we have is slot angle. The phase difference contributed by one slot in degrees electrical is known as slot angle, and it is denoted by beta. So one slot angle is equal to 180-degree divided by N. N refers to pole pitch. If we consider an induced EMF in a conductor which are placed in a slot adjacent to each other, there will be a phase difference of beta. So out here we can see that the EMF induced in conductor 1 and the EMF induced in conductor 2 has the angle difference of beta. Next important term in armature winding is coil span factor or pitch factor, which is denoted by Kc. It is defined as the ratio of the voltage generated in the short pitch coil to the voltage generated in full pitch coil. So out here Kc is equal to actual voltage generated in short pitch coil divided by actual voltage generated in full pitch coil. So after doing the simplification, we get the formula for Kc is equal to cos alpha divided by 2. So the next term we have is distribution factor, which is denoted by Kd. It is defined as the ratio of EMF when the coil is distributed to the resultant EMF when the coil is concentrated. It's always less than 1. So out here we have a small derivation of formula for distribution factor, which is called to EMF generated when coils are distributed to the over EMF when coils are concentrated. So to calculate it, we have some other terms like M, which stands for slots per pole per phase, which is calculated by M is equal to slots divided by pole time phase, and beta, which we already know is the slot angle. So after using all these formulas, we get, after simplifying all of them, we get the formula Kd is equal to sine M beta divided by 2 and over M sine beta divided by 2. So M out here stands for slots per pole per phase, beta stands for slot angle, and N stands for slots per pole. So next we have is types of winding, which is concentrated and distributed winding. So in concentrated winding, all the turns of the coil are wound together in a single coil. Moreover, in concentrated winding, all windings belong to one phase are placed in one slot under every pole. Next we have is distributed winding. In distributed winding, the turns of the coil are distributed across multiple coil slots. This reduces the current and voltage stress and can improve the performance and efficiency of the machine, especially in high power application. However, it is more complex and costly to manufacture compared to concentrated winding. And the next we have is a single layer and double layer winding. Single layer winding, each coil or windings occupies only one layer on the core, with one coil set per slot. It is simple and cost effective, but may have limitation in performance. Double layer winding, it consists of 2 coil sides or layers of winding per slot, offers better space utilization and improved performance, commonly used in high performance electrical machines like transformer. And in most of the armature winding, double layer winding is preferred over single layer windings, and it is used in most of the armature windings. So here comes to the end of my topic, and thank you and have a nice day.